Hello and welcome back. Today we will be studying VSEPR theory, which is nothing but valence shell electron pair repulsion theory. It talks about the effect of valence shell electrons present around the atoms and their contribution towards the bonding, especially its contribution towards the shape of the molecule. The main concept of this valence shell electron pair repulsion theory or VSEPR theory deals with the shape of the molecule. So generally in the exam, the question will be like, if I have this many amount of valence electrons, then what will be the shape of the molecule? So we know what is valence electron. The valence electron is either bonding electron, bonding pair of electron, or lone pair of electron. Lone pair of electron is one. For example, you take the example of H2O. In H2O, we have bonding pair of electrons. These are nothing but the electrons which are taking part in the bonding process. And we have lone pair of electrons. These are the electrons which are not taking part in the bonding process and they are freely or readily available on the atom. And these are shared between the atoms. This is solely present on one atom, the lone pair. And these lone pairs and these bond pair interact and they will decide the shape of the molecule. The VSEPR theory can be studied in terms of different postulates or different guidelines, we can say. The first guideline reads, the shape of the molecule depends upon the number of valence shell electron pairs, both bonded and non-bonded. Non-bonded means lone pair, around the central atom. This is what we have discussed. A central atom can have lone pairs or central atom can have bond pairs. It can have both. It can have only bond pair or it can have both bond pair and lone pair. The interaction between these valence shell electrons will decide the shape of the molecule. The pairs of electron in second postulate is the shape of electron. The pairs of electron in the valence shell repel one another. Since we know electrons are negatively charged, we know this, and we know like charges repel. Since electrons are negatively charged clouds and the like charges repel, the electrons which are present in the valence shell repel each other, and this repulsion will give a definite shape to the molecule. And these pairs of electrons tend to occupy such position in space that minimize the repulsion. That is obvious because in any structure or in any state, the material or the component which is present, here we have a molecule which is a component, it tries to attain least possible energy state. This least possible energy state can be achieved when the repulsion is extremely minimum. When there is a minimum repulsion is present, they can be highly stable. That is why these pairs of electrons tend to occupy such positions in the space that minimizes the repulsion and maximizes the distance between them, which leads to least energy state. The valence shell is taken as a sphere with the electron pairs localizing on the spherical surface at maximum distance from each other. This is just a reiteration of the sentence. They want to be present at a maximum distance away from each other such that they can have a stable conformation. A multiple bond is treated as if it is a single electron pair, and the 2 or 3 electron pairs of a multiple bond are treated as a single super pair. That is like you have a bond like this, you have 2 bonds. That's why you have 2 electron pair here, 2 electron pair here. So a multiple bond is treated as if it has a single electron pair. So 1 electron pair and 1 electron pair. Where 2 or more resonance structures can represent a molecule, the VSEPR model is applicable to any such structure. The resonance structures are, for example, in case of benzene. The resonance structure of benzene is this. Benzene can have a structure like this, or benzene can have a structure like this. Okay, this is called as resonance structure. They have a similar energy structure and they will be oscillating between these two. When those kind of structures are present, you can take either this or this. These are the different postulates of VSEPR theory. In a nutshell, VSEPR theory is nothing but the arrangement of valence electrons at the bonded and lone pair of electron, and it deals with the arrangement in such a way that they are arranged far from each other, that is at the maximum distance, so that the energy can be minimized and molecule becomes stable. And how the interaction will be? The interaction can happen between lone pair and lone pair. For example, you have oxygen. I'll take a classical example of water. If I have a oxygen lone pair on the oxygen and a bond pair between oxygen and hydrogen, the interaction between these lone pairs will always be higher because it is intuitive. See, the lone pair of electrons are completely free. They are not participating in any bonding. That's why their interaction will be always higher and leads to maximum repulsion. So lone pair interaction will be higher compared to lone pair bond pair, then compared to bond pair lone pair. The lone pair is highest, then lone pair and bond pair. This gives you one clear indication: when there is more lone pair is present, molecule will obtain more bent conformation. That is why the bond angle in ammonia is lesser than bond angle in water, is lesser than bond angle in bond angle in ammonia is greater than bond angle in water, because the ammonia has only one lone pair of electron. That's why the bent is less. But in case of there are two lone pair of electron, the repulsion is more, hence water is more bent. If you take CH4, it has a perfect tetrahedral structure because there is no lone pair of electron, hence the bond pair repulsion is weak. We get a perfect tetrahedral structure. So based on this knowledge, let's see different examples. First, let's see if there is only the interaction can happen two ways. That is, molecules can have a lone pair and bond pair, or molecule may just have a bond pair. There will be two scenarios where there is presence of both bond and lone pair, and that is the molecules in which central atom has no lone pair, and there is central atom which has one or more lone pairs. First, let's see if there is no lone pair is present. There are only bond pairs, then how will be the structure? See, let's take for example two electron pair. You have a structure like beryllium chloride and mercury chloride. There is no lone pair present, only bond pairs. They present at a 180 degree to each other. If this is a material X and this is the atom X and there is Y, yeah, there's a linear structure. There will be 180 degree from each other. You have a linear structure. If you have three bond pairs and there is no lone pair, they will attain a trigonal structure. They will be placed around at an angle of 120 degree, which is the farthest angle. There will be no bend or distortion present in the system. And if you have a 4, you have a classic structure of tetrahedral. For example, you have a methane. Here there is no lone pairs. There are completely bond pairs, and we know bond pair interaction is weak, and we have a perfect angles like 180, 120, and you have a 109 degree, 5 minutes of tetrahedral structure, etc. And we have 5. We have trigonal bipyramidal, that is 3 in the plane, 2 in the above, 2 1 each in the above and below the plane, and you have an octahedral structure. These are perfect structures without any distortion. But when you introduce lone pairs, the distortion starts to occur. For example, if you have a structure called AB2E, that is 2 bond pairs, I'll write this is bond pair and this is lone pair. If you have 2 bond pair and 1 lone pair, if you have 2 bond pairs and 1 lone pair, we have seen previously, if there is only 2 bond pairs, no lone pair, they will be linear. This should have been the structure X, Y, Y here. But now we have a lone pair like this, and we know lone pair here interaction will be there, and lone pair bond pair interaction will be here. So this will be starts pushed like this. You have a linear like this, but there is a lone pair here, so it starts pushing like this, the lone pair, and you obtain a bent structure of a trigonal planar. Trigonal planar should be the structure, but you get a bent structure here. And then when you come to AB2E, AB3E, when there is a 3 bond pairs and 1 lone pair, like ammonia. Technically, it forms a tetrahedral, that is 1, 2, 3 bond pairs and 1 lone pair. But you know, lone pair and bond pair interaction is higher, so it won't be a regular tetrahedral, because this bond pair, this lone pair, pushes the bond for further. This will be like this and push it closer. Means you have the decreased bond angle between these two. The bond angle is decreased from a regular tetrahedron. Regular tetrahedron should be 109 degree, 5 minutes. It is decreased. Why it is decreased? Because there is a stronger lone pair bond pair interaction, which we have seen. So we call it trigonal pyramidal structure, case of ammonia. Then we have AB2E2, that is 2 bond pairs and 2 lone pairs. This is in case of water. See, we have seen when the 2 bond pair and 1 lone pair is present also, it forms a bend, because it should be a linear, but it is bent. Now the bend becomes much further because we have 2 lone pairs, because lone pair interaction is higher. The bend was like this when there was this particular system AB2E, it was bent was like this. Now it increased more. The bend becomes AB2E2. The bend is more. Here the bond angle was more. Here, as you can see, bond angle decreased further. It was higher bond angle. Here it is lower bond angle, and this is also a bend structure. Now comes to AB4E. AB4E, we have a seesaw structure. This is X bond here, bond here. This is like this. This means You have a structure like this. You have a like I can show it like it's a seesaw structure. It's on the straight line. It's on a single plane x, y, y, and these are going one direction. One is coming out towards. One is going away. That is, you have bond like this. This is one center electron, center atom, two atoms here, and you have like this. One is coming towards you. One is going away from you. This is your seesaw structure, and above that there will be a lone pair. Why this is happening like this, giving the legs to this structure? Because the interaction between lone pair and the bond pair, the higher interaction between lone pair and the bond pair. Again, when you go to AB3E2, 3 bond pair and 2 lone pair, you will have trigonal bipyramidal structure. In that case, where the lone pair of electron is present in a trigonal bipyramidal, for example, you have a trigonal bipyramidal is this trigonal in the base and bipyramidal. The lone pair will be always present in the planar, not in the these positions. It is present in the plane only, not in the axial position but in the planar positions. So this is, we also know called as T-shaped system. That is, it forms like this. Since it is called T-shaped compounds. And next is AB5E, which is nothing but square pyramidal. That is, square is the base, and at the one axial position you have lone pair, which is almost similar to the octahedral structure. And then finally we have AB4E2, which is also similar to octahedral structure, but the regular structure will be seen as square planar. But again, you have to keep it in mind, it is not a regular square planar. There will be distortion in the bond angle, because in a regular square planar there will be no lone pair of electrons. Since there is a lone pair of electrons, there is an increased interaction, that is increased repulsion between lone pair and bond pair. So this B, the atom B here pushes it like this, like as I shown in the Bend's case. The bond was like this. When a lone pair comes here, it starts pushing it. It starts pushing, the bond angle starts decreasing. Like this here also, the bond angle starts decreasing. So this is the different kinds of interaction which is happening when you have a lone pair and a bond pair. So you have, what you have to do, you have to compare the, when there is no lone pair, what happens? When lone pair comes, what happens? If you have to keep that in mind, when the lone pair starts coming, the lone pair starts interacting, and the main thing what lone pair do is lone pair repels more as you compare to the bond pair. Due to this increased repulsion, the bond angle starts decreasing. So as the number of bond lone pair increases, the bond angle starts decreasing and start distorting from the perfect, like tetrahedron, octahedron, from that perfect shapes it starts distorting. So I hope the concept of VSEPR is clear to you. In the next class we shall see about the hybridization and associated concepts. Thank you.